All right, so we talked about in the end of the last video how dipole-dipole interactions are intermolecular forces between molecules uh, that are polar, where there's a permanent dipole. Okay, and so we're asking the question: do water and dichloromethane exhibit dipole-dipole interactions? So we're going to have to calculate the difference in electronegativity of each of the bonds, and then figure out the shape, right? And figure out if there's a net dipole in the molecule, and then whether or not the two molecules have that net dipole. If there is, then they can have dipole-dipole interactions, right? So the bonds in dichloromethane is CH2Cl2. So there's carbon, hydrogen, and chlorine. There's carbon-hydrogen bond. That's going to be nonpolar because that has a difference in electronegativity of 0.4. Remember, less than or equal to 0.4 is a nonpolar covalent bond. Chlorine and carbon, that's going to have a delta of 1. So that's going to be polar covalent. And oxygen and hydrogen, that has a delta a difference in electronegativity of 1.4. So that's going to be polar. And so we can draw the Lewis structures of these. I trust that you can do this. It's basically a tetrahedral shape for dichloromethane, and it's bent for water. We've gone over that one before. And so, yes, there's an overall dipole for these, right? How is this going to look like? Well, there's an overall dipole for oxygen pointed this way, right? And so this is going to have a partial negative charge, and the hydrogens are going to have a partial positive charge, right? And then for chlorine, that is more electronegative than carbon. The hydrogens don't really have any dipole. And so your net dipole, there's going to be an individual dipole going this way for each of the chlorines, but your net is going like that. And so, yeah, the way that I oriented these molecules is correct. The positives, slight positives of the hydrogen are going to be attracted to the slight negatives of the chlorines in dichloromethane. Or the molecules could be oriented like this, right? Where you have a negative on the oxygens and a positive on this side of the dichloromethane molecule. Hydrogen bonding is another type of intermolecular force. And this is basically it's an extreme version of a dipole-dipole interaction. And it's just extreme because you have really electronegative atoms, nitrogen, oxygen, and fluorine involved, and you have hydrogen, which is a very small atom. So it really kind of feels the effect of this dipole. Dipole can kind of travel through space. You know, it's a Coulombic type interaction, charges, right? Charges, you might know from physics, charges go as the square. So the further apart they are, they dramatically drop off with distance. And so if you have hydrogen, which is a very small atom, the smallest atom there is, you can then have much stronger dipole-dipole interactions because hydrogen is very small. And so the charges can basically get closer to one another. So if you have nitrogen hydrogen bonds, oxygen hydrogen bonds, or fluorine oxygen bonds, i.e. the three most electronegative elements with hydrogen, you'll get very strong intermolecular force, very strong dipole-dipole interaction that we call a hydrogen bond. Hydrogen bonding is key to how DNA stacks. It explains why DNA has a helical structure. There's basically hydrogen bonding between the different DNA bases. It also explains why ice has a certain structure that makes it less dense than liquid water, which is very important, right, for all of life, because that means that ice floats, and so fish can swim underwater even when the top of a lake is frozen. So there's a lot of important ramifications for hydrogen bonding, too many to mention.